Donut Lab Test 4 just came out, and this time, instead of VTT testing in the lab, we have an actual motorcycle, the Verge motorcycle that will ship with this battery first, at a public charger, actually charging over 5C, faster than anything we have on the road today. But what's really interesting is now that we have this data, including test 1, we can actually start drawing some lines and some comparisons and see just how remarkable this battery actually is. This was surprising. I'm Ricky, and this is 2-Bit Da Vinci. This video is brought to you by Surfshark. Now, we're 4 tests into this investigation, and I want to be upfront about what we still don't know. They've never weighed the cells, so we still can't validate their 400 watt-hour per kilogram density claim, and the 100,000 charge cycle claim, again, unverified because we only have about a dozen tests or so. And finally, the chemistry, still we don't know. I mean, we're seeing more and more information, but we don't have a complete picture just yet. So what do we have? We have real-world charge data from a motorcycle at a public charger, plus VTT lab data from test 1, where the same cells were tested at 5C and 11C with precision instrumentation. When you overlay them, you can see exactly who's riding each part of this charge curve. The BMS, the cooling, and the chemistry each tell a different part of the story. So this is their data, and as you can see here, the test starts at around 9%. The C rate climbs all the way to about 5.7, and it pretty much holds it. There's a little dip here, but it holds pretty much an identical rate all the way through to about here, dips up a little bit, and then it starts to taper around 43% state of charge. Then it dips down to another little plateau here until finally it tapers all the way down to 80%. First thing to note is their test was starting around 9% state of charge. I would have loved to have seen 0 to 100, but we don't have that. All we have is 9% to 80%. And by the way, the blue line here is the Lucid Gravity, which is kind of the fastest charging EV we have in the US right now. Within a minute, the pack ramps up to 103 kilowatts, a 5.7 C charge rate at the pack level, and held it flat for nearly 5 minutes. And that got the pack from 10 to 50% in about 5 minutes, 10 to 70 in 9, and 10 to 80 in 12 minutes, which is incredibly quick. 103 kilowatts might sound small next to like Lucid's 400 kilowatt fast charging speed, but a big battery at a low rate hits high voltage easily. What matters is the C rate. Like if you have one battery and you can charge it with this much amount of electricity, when you add 2, you can double the electricity going in. It doesn't mean each cell is any better at charging, just you have more of them. So a really big pack means more power in, more power out more easily. This was on an 18 kilowatt-hour motorcycle battery. Now for context, other electric motorcycles I've seen, like the Zero motorcycle, for example, charges at around 12 kilowatts, and the very best I've seen is around 25. So this is between 8 and 4 times better than the best motorcycles. The Lucid Gravity, the line here in blue, has a 116 kilowatt-hour pack. It's liquid cooled and has a 924 volt architecture. This is like the best in the business right now in the US. And it peaks at 3.2 C. This little motorcycle hits 5.7 C, nearly double. And it's not just a peak. At 30%, 50%, and 70%, the Donut battery sustains roughly twice the Lucid's rate across the entire session. Comments on Donut's videos claim that other makers like BYD and CATL already achieved 3 and 4 C, but you got to remember that they have massive liquid-cooled battery packs. And I think with the new Naxtra batteries from CATL with sodium ion, you might even see faster charge rates than that. But it's not apples to apples because this is a motorcycle with air-cooled battery cooling. Now, to keep myself honest, 3 videos ago I said the real-world rate of charge will be closer to 5C with a 12-minute charge time. And that's kind of what we're seeing. 5.7 even better, but around the realm of what I thought. Because when you put it into a pack, you're not just blowing up a battery at 100 degrees Celsius. You have to maintain some level of control with the BMS that you're comfortable with. And as an OEM, you're responsible for the warranty of your battery pack. I've been researching tech like this on my channel now for nearly a decade, and I couldn't do this without all the insights I've learned, especially on travel. We're going to China for some special episodes next month, and our sponsor is Surfshark VPN is going to be vital. I use Surfshark VPN to hide my true IP address. It's like meeting someone to sell something on Craigslist at a coffee shop instead of your house. Better to keep that private. In China, many American services like YouTube will be blocked, but hop on Surfshark VPN and it'll be like you're at home. Choose different locations when shopping for deals online and you might be surprised at how much the prices differ. It's like calling a plumber when you live in Beverly Hills versus somewhere more affordable. On trips, I often use public Wi-Fi, but with Surfshark VPN, all your traffic is encrypted, so even if bad actors are trying to steal your data, your passwords, or anything else, they can't. Why I love Surfshark in particular is because it supports unlimited devices. So whether I got my iPhone or iPad or laptop, I'm safe. Plus, with over 4,500 servers in 100 countries and no log VPN service, your options are massive and your online activity is safe. They even have other great security products like Surfshark Antivirus. So if you've heard about VPNs and you've been curious, you're going to love Surfshark. Go to surfshark.com/2bit or use coupon code 2bit at checkout to get 4 extra months today. Huge thanks to Surfshark and you. Now back to the show. So to put this into perspective, like how killer this charge curve is, what if we took the donut battery in a motorcycle and scaled it up to the size of the Lucid pack, for example? So there's 2 ways to look at this. First of all, if instead of charging at 3.2C like the Lucid did, if we got the full 5.7, we'd be hitting 686 kilowatts of charge speed. Nearly double, right, from the Lucid's 375 or so. That is insane, and no charge that we have today can support that. Now, I wanted to give you a sense of what this would look like, right? To 20%, it would take 4 minutes and 30 seconds on the Lucid today, and if it had the donut pack, it'd be 2:45. And by the way, I'll make these graphs available for you guys to play with and check out. All you gotta do is join our newsletter, and we'll share all this with you. Now, at 50%, the donut pack in a Lucid Gravity would charge 5 minutes and 36 seconds faster. Now, to 80%, the Lucid Gravity with the donut pack would only take about 12 minutes and 30 seconds, nearly 14 and a half minutes faster than its current pack in half the time. So this is really the context. If you're going to get a car and it had this donut pack in it, you could charge to 80% from 0 in 12 minutes instead of 26. That's the difference between taking a little restroom break and grabbing a bag of chips and having to sit down to like a full lunch. That is pretty significant and a real quality of life improvement. One fact about every battery ever made is that charging gets harder as it fills. Think about a parking lot. When it's empty, you pull into any spot pretty much instantly. But as it fills, you're weaving around traffic and looking for open spots. It's kind of the same with batteries. Ions inside a battery do the same thing, finding open slots in the crystal structure and running out of easy ones as state of charge climbs. Multiple forces all push one direction and it slows down. Ions run out of room, voltage hits the ceiling, and the heat starts building up following one equation. Heat equals current squared times resistance. And the squared part changes everything because doubling the charge rate quadruples the heat. Going from 1C to 5C isn't 5 times harder thermally, it's 25 times harder. And going to 11C is 121 times harder. And that's why every fast charging EV uses liquid cooling, and why an air-cooled pack at 5C for nearly 5 minutes is nearly unheard of. All these forces say that the curve should taper smoothly. Now, this is the data from a DC fast charge test from State of Charge, one of my favorite YouTube channels for everything DC fast charging in terms of testing. If you want to nerd out, definitely check out State of Charge. But you can see that the charge power climbs to up into the 350s, but it takes a while before it actually reaches its full. And now this probably is because the pack wasn't warmed up. So when the pack reaches full temperature, it reaches its best charge rate. But then around this point, it starts to taper. So you can see this tapering down line. And then there's a little dip here. I think Tom from State of Charge mentioned that this might have been from the charging station and not from the car. And then you can see that it tapers further. But it only holds that really high level for a very short amount of time. It's already under 300 kilowatts by like 38%. And then it's under 200 kilowatts by 50%. So even at a 400 kilowatt charging station, you're only actually getting those kinds of charge speeds for a very, very brief amount of time. And it's the same on my Tesla as well. So that's the original data. This is the simplified version of it. Now, all those forces tell us that the line should taper like the Lucid graph. But the donut curve isn't a taper, it's a staircase. And the VTT lab data tells us why. The first author of this data, if you will, the first actor, is the BMS. The flat peak of 103 kilowatts from 13 to 45% is like a straight line. Never 104 and never 101. It's a programmed power ceiling. In the VTT lab, the cell took 286 amps from the very first second with no ramp and no hesitation. and the cell accepted it immediately. The motorcycle took 37 seconds to ramp to 103 and capped at half the cell's proven rate. At 5C in the VTT test, the cell with one heatsink held constant current all the way to 87% state of charge. The hotter the cell got, the lower the internal resistance dropped, and the longer sustained full power before voltage forced a taper. The motorcycle held it to 45% before the BMS pulled the plug, not because the cell couldn't keep going, but because the pack ran out of thermal headroom. So right here, you can see that something happens here where now you start to taper down to a lower level. But based on what we see from VTT test 1, I think this right here is thermal related. Think of this like a ship with a leak in it. If you have a bucket and you're pouring out water as quickly as the water is coming in and you're dumping it out, you can stay afloat. But if the water's coming in faster than you can dump it out, you're going to start to capsize. It's the same thing. Any system has a cooling capacity, how quickly it can dump heat. The bigger the radiators and the heat sinks, the higher that capacity is. So for this Donut Lab Verge motorcycle with air cooling on both sides of the pack, there's probably a limit. And Verge has probably set a limit for how hot they want this cell to get for their own internal reasons. It could be unrelated to what the Donut Lab battery cell could actually sustain. So when this limit, let's just make up a number. Let's just call it 60 degrees Celsius. Let's say it hits that temperature right here. The BMS is programmed to lower the current to then bring that temperature down. And then it continues to do that until the temperature reaches equilibrium, meaning that the pack's ability to discharge heat out of the pack is the same as the input heat coming in from the charge rate. Then it holds that for a little bit longer. So this again is kind of a flat line. So there's probably a next set point where it charges it here. Now this is probably the equilibrium, meaning that the cell could charge at this rate forever and the heat coming in and the thermal capacity of the motorcycle is equal. So electrical chemical limits are tied to how full the battery is. This drop is tied to the clock, a temperature threshold where the BMS is watching a thermometer cross a line and then ratcheting current down in real time. The thermal math confirms it. In the VTT test, a single cell at 5C with one heatsink reached 61 degrees in about 8 minutes. Now, 50 cells packed together with only air cooling could reach that limit faster, although the motorcycle has fans, right? So it has active cooling, whereas the VTT test was just a heatsink sitting on top with passive cooling only. So we have data point 1, a BMS limitation, right? The cell is just strictly sticking to what the BMS is providing it. The cell could go higher, but it isn't. It's just capped right there. Then I think we have thermal considerations in the BMS, and the BMS is throttling power to maintain it. The third author is electrochemistry, and it only shows up at the end. The final taper from 71 to 80% is the only part of the curve that looks normal, like a graduated, smooth slope. The cells are approaching their 4.3 volt ceiling. Remember in test 1, we talked about how constant current and constant voltage charging works. Once you reach a certain level of voltage, it becomes a constant voltage situation where you keep the voltage capped and you taper the current to maintain that current all the way to full. That is what's happening here. So this is the only part that is cell dependent. Everything happening here is about the pack and the Verge motorcycle, not the donut battery. Okay, now for the really fun stuff. The cell handles 11C and the motorcycle runs at 5C with air cooling. So what happens with a liquid cooled pack that was a Lucid Gravity size? Donut C rate applied to a Lucid Gravity sized 120 kilowatt hour pack gives a peak of 686 kilowatts all the way up here. Now this isn't realistic because the charger that he was charging this car at was a 400 kilowatt charger, so it couldn't even support this. But CATL and some other companies in China are introducing megawatt and 1.5 megawatt chargers. So there in the future, we might see that. But I wanted to show you just what 5.7C, which is what the Donut Lab test was on the motorcycle, looks like scaled up to a Lucid Gravity. Huge fat charge curve all the way over to about 45%. The real Gravity today picks up steam all the way to about here. And I think the reason why is probably internal temperatures. If you ever have preconditioning, batteries like to be at a certain temperature to reach their max charge rate. That happens probably here. And then it starts tapering down. But the donut pack in a Lucid Gravity with liquid cooling could keep on going all the way to about here. So at 45% state of charge, which is, we're just taking that data from the motorcycle, you'd get here in about 5 minutes, 20 seconds instead of 10 minutes in a traditional Lucid. 4 minutes and 45 seconds faster. And all the way, you're speeding up, you're getting there faster and faster. And to get to 80%, which is what I would do if I was road tripping this car, I'd charge to 80%, unplug, and keep driving. Because that last 80 to 100% takes forever. But to 80%, you'd get there in about 12 minutes instead of 26 minutes like you could today. 14 minutes faster. So this Lucid Gravity, which is like the best road tripping car in the US right now, with a donut pack, would be like gasoline stop levels of fast. That's why this test matters. It is wild. I mentioned that this data is not really reflective because you're limited not by the car or the pack, but by the infrastructure, by the charger. And I don't see 700 kilowatt chargers coming to the US anytime soon. Now, to make this more realistic then, what if instead of charging at a 5.7 C like we do in the motorcycle, let's keep charging it at the Lucid Gravity level today, right? 3.2 C. But this graph shows you what that would look like if we could keep that charge. Like we mentioned before, the Lucid had to build up temperature to be able to get to this max charging rate, and then it started dropping off right away. But our donut pack doesn't have to do that. So we can get all the way to about 70% before any tapering happens. Because remember, in the other simulation that I showed here, this drop and this drop is all still above 400 kilowatts of speed. So even though that this drop happens from 600 to 400, when you just charge at 400 like a traditional battery might, that extends all the way here to 70%. That means to go from 0 to 70% in a Lucid Gravity at a 400 kilowatt fast charger like a Tesla V4 charger. You could do that in 14 minutes instead of 20 and save 6 minutes. And all the way to 80%, it would be nearly 10 minutes faster. So this pack, in terms of like road tripping, if you're a big road tripper or a public charging user, this would be a huge game changer and would save you tons of time on charging. Being at test 4 at this point and covering this as much as we have, one theory that we talked about in the very early, like first test, first unveil, was what if it's a hybrid battery with a supercapacitor and a chemical battery kind of stuck together? That could potentially, and I was thinking about this early on, explain these two plateaus. It looks like there's something happening here, and then it has to dip to like a state 2, right? And then it holds that. What if this first part was a supercapacitor where you're storing on the plate on a surface, which happens very quickly. And when that fills up, we then taper down to an intercalation of ions via a chemical process in a chemical battery. But based on what we know about how fast this battery can charge, I don't think that's it. I think this is just a BMS holding a charge level well below the battery's potential limit. So we're 4 tests in, and here's where we stand. Verified, 11C cell level, 5C pack level, with 100-degree survival, air cooling at temperatures that need liquid cooling traditionally, and a charge curve where the cooling system is the bottleneck rather than the chemistry. So you're limited only by how well you could cool these packs. Theoretically, we'd have to wait to see how temperature affects degradation over time, and that 100,000 charge cycles, what is that based on? Is it based on 50 degrees, 100 degrees? We have to find out all those pieces to put that entire thing together. Also, Donut mentioned that the BMS is still in early development. The BMS is what handles that curve and says, okay, the temperature and the charge rate and the current, we're going to play with these parameters to keep the battery healthy. That's the brains of a battery charging system. And they mentioned that Verge, I think, is still developing it. So these curves and flat spots and stuff we're looking at, these just might be early BMS signatures that'll eventually smooth out over time. We'll have to wait and see, but that could just be preliminary data. But what we found is pretty damn remarkable. These are numbers that are not common. It is not common to see a pack charging at 5.7 C with air cooling. And we're not used to seeing 103 kilowatts being delivered to an 18 kilowatt hour battery pack. The way we charge cars faster today is with having a battery pack that's bigger. My Tesla Model S has a 100 kilowatt hour battery pack, and the fastest speeds I've seen are about 220 kilowatts, so about a C rate of 2.2. The Lucid Gravity goes to 3.2, which is even better. Some of the BYDs and CATL base cars can go higher, but we're talking about a 5.7 C air-cooled battery on a motorcycle that is planned to be shipping this year. That is pretty damn wild. Now, One of the funnest things about doing these videos is getting a sense of where the audience, where all of you are. So this is maybe my favorite part about this whole thing. Let's talk about the comments that I've seen so far. I'm filming this around noon, so any comments that came into their video after noon aren't going to be here. But we're looking at around over 200 comments, 190 top likes, 10 key themes that I've identified from all of these videos, and 20 questions that you could potentially answer. So the comments are about 30% positive, 20% skeptical, and 30% negative, like they're calling it a scam or something like that, and 20% neutral. This actually is becoming more evenly distributed. I think it was way more negative and skeptical earlier on, and these numbers are actually becoming more optimistic, which kind of makes sense. They're on test 4. Let's talk about the top recurring themes. Number 1 has been the same since the very first episode, the weight of the battery. Over 30 comments pointing out that the energy density hasn't improved. Very true. Number 2 is that they're impressed by the charge speed. Anybody who's watching a video on battery charging is going to be sophisticated in the industry, and they're right. This is really impressive. They want to see the cycle life data. 100% agree with you. This right here is what they should do next. Over 10 comments is why no VTT this time? And people have mentioned that, that seems fishy. There's nothing fishy about that. VTT is purely laboratory testing, right? That is like at a pouch level. This is pack level, when you manufacture it into something with cooling built into a motorcycle. So this is actual real world testing at a public charger, not some controlled lab environment. Cold weather testing, I'm still waiting for that too. I think that would be very telling for chemistry. And there's a bunch of comments, over 10, about BYD and other Chinese makers in comparisons to this not being that special or important. But I disagree with that, I think. And over 8 comments point out, why not charge at 11C? Why has it dropped to 5? I think this is actually pretty understandable as well. A 1,000 horsepower car spends less than 0.00001% of its life at 1,000 horsepower output. Most of its time it's at 200 or 300 horsepower. Same thing. Just because it can go to 11C doesn't mean it will all the time. And then finally is that they want cars and e-bikes and talk about scaling beyond the motorcycle. That is interesting. It tells you people are starting to think about this in products, right? Now, questions that we could answer. How does this compare to the fastest charging EVs like Lucid or BYD? Well, 5.7 is on the very high end for a pack level charge. Like we mentioned, the Lucid is 2.3, and some of the Chinese brands, I don't have like data in front of me, so it's hard to tell, but they're probably in that range as well. Probably better than Lucid, maybe a little less than Donut. The reason why I did that Lucid Gravity comparison earlier was because there were a lot of questions about what would this mean in an actual car. I was curious too. Hopefully that gives you guys a lot of insight on that. So now this is the most engaged comments. This had 190 likes. This says 100 kilowatts of charge speed in a 20 kilowatt, 18 kilowatt hour pack is amazing. My Zero SRF charges at 12 kilowatts and the Energica charges at 20 kilowatts, but over 100 is insane. Very true. Small pack, fast charging is very impressive, high C rate. Whatever kind of battery chemistry, this is pretty darn good. Going from 9 to 80% in 12 minutes is really impressive. Agreed. Another comment and another sentiment I've seen is give a vehicle to Bjorn, who has a YouTube channel, or like Sandy Monroe. Give it to us. Give it to Zeroth and I. We'll rip it apart and do some testing as well. And they're saying that they need to see that to believe it. Other questions are about future tests. There is a clock to another test next week, so we know there's another test. We know that there were 3 cells sent to VTT, and they've all been used. This was a real-world test. I'm guessing the next test will be the same thing, maybe Verge motorcycle or something else, but it won't be a VTT. So yeah, this is what they want to see. We'll share all this with you guys, and that is a look at what people are saying. This is pretty impressive, and I can't wait for next week. Donut, good job. I was underwhelmed in test 3. I kind of mentioned that. I'm excited again for this one in test 4, because again, that's a motorcycle that they drove to a public location and charged it. Now, what do you think will be in test 5? I want to know below. As always, let's make this a live and living comment section. Tell us what you think they'll do in future tests and how impressive this test was to you. All right, until next week, I'm Ricky Da Vinci. Thank you so much for watching.